So we're going to talk a little bit about angular momentum. If you remember the definition for linear momentum, we used linear momentum was just p equals mass times velocity. Technically, it was a vector. Not technically, it's a vector. So we can develop an analogous equation for angular momentum. And so angular momentum is given the designation L, the letter L. And if we use the rotational equivalent of mass, we have an I here. And if we use a rotational equivalent of velocity, we have angular velocity here. And so in one dimension, we just say L is equal to I omega. And so if you want to know the angular momentum of something, you can calculate that from its rotational inertia times the angular velocity. And so, for example, we could say, what is Earth's angular momentum? Right. If we assume the Earth is a solid sphere, then its rotational inertia is just 2/5 mr squared, which is 2/5 times 6 times 10 to the 24th kilograms, because that's the mass of the Earth, times 6.38 times 10 to the 6th meters squared, which gives us 9.72 times 10 to the 37th kilogram meter squared. And so if we wanted to calculate its angular momentum, we'd need to use omega, right? We need to multiply this by omega. Omega is equal to 1 revolution per day, right? The Earth rotates, or rotation per day. But then we want to convert it into radians per second maybe, and so it would be times 2 pi radians per revolution, right? Times 1 day over 86,400 seconds, right? That's 24 times 60 times 60, right? 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute. And if I evaluate all that, I get 7.3 times 10 to the minus 5th radians per second. This is a result we calculated previously, right? And so then I can calculate the angular momentum, which is 9.72 times 10 to the 37th kilogram meter squared times 7.3 times 10 to the minus 5th radians per second, which gives me about 7.1 times 10 to the 33rd kilogram meter squared per second. Those are the units of angular momentum. We don't really give that a name. And so that's the angular momentum of the Earth. So we're going to talk about angular momentum and torque. This is sort of still for rotational motion, but if you remember, for translation, in other words, for basically for linear motion, we had the force is equal to the mass times the acceleration, which is equal to the mass times the change in velocity over the change in time. But mass times change in velocity was just the change in momentum, and so the force was equal to the change in momentum over the change in time. And this is really the way Newton wrote it. For rotation, we replace force with torque, and we replace mass with rotational inertia and A with alpha, and so that gives me I times delta omega over delta t. But we already said that I times omega is the angular momentum, and so this is just delta L over delta t. And so this is how the angular momentum is related to the torque. The torque causes a change in angular momentum. And so we can just do an example. A disk what is its change in angular momentum? And so we can just grab this equation and say, we can say the torque is equal to the change in angular momentum over the change in time, or the change in angular momentum is equal to the torque times the change in time. This is kind of like an impulse type equation. Remember, we had the change in linear momentum is equal to the force times the change in time, and we call that the impulse. And so in this case, the torque is 25 Newton meters times 2.5 seconds, which is 62.5 Newton meter seconds, which is 62.5 kilogram meter squared per second.